Yeah.
Okay. Hello, everyone. Thank you for attending this virtual numerical analysis seminar talk. Today, we're very happy to have Dr. Koffi, Enakoutsa, and Xinghao Dong to tell us about the Morrey Conjecture insights from numerical simulation on quasi-convexity and rank 1 convexity. So Koffi is currently an assistant adjunct professor at UCLA Math Department. He got his PhD from Sorbonne University, Paris in 2019. And then Xinghao is a student from UCLA. And today they're going to give us a joint talk on this topic. And the floor is yours.
Thank you very much, Professor G, for the invitation and for helping us with this seminar on the Morrey Conjecture. Yeah, I'm Koffi Enakoutsa, and like you said, I work as assistant agent professor at UCLA in the Math Department.
And I am Xinghao Dong. I was a student at UCLA, and I will be joining University of Wisconsin Madison to pursue my PhD degree this fall.
So our talk will mainly revolve around a few points. So I will start by presenting what Morrey Conjecture problem look like, and leave the floor for Xinghao to present the numerical strategy that we come up with, plus the result that of the finding or the outcome of the numerical methodology we use. And then next, I'll come back and present the validation of this numerical approach and discuss the results with respect to what the findings were before we came up with this research. And then I'll leave Xinghao wrapping up the conclusion of the work and give some future direction for this type of research. So let me start by saying that in the 1950s, Charles Morrey was facing a question of well-posedness of this optimization problem. So he wanted to look at what are the correct notion of convexity on the function f by abstracting properties such as growth or smoothness on the function f. So he was solely interested in what are the convexity property on the function f such that this minimization problem is a well-posed one. Are there minimizers on this? But as you know, convexity of a function will is extremely useful when you deal with the minimization of this problem, because if the function were convex, then we will have yield a global minimum in such context. But for practical application that involve this type of minimization problem, the practical example are in nonlinear elasticity, hyperelasticity for the most part, where the material don't behave in small deformation, but large type of deformation. So in that context, the notion of convexity become very rare. So, but there are several weaker notions of convexity that can be used to characterize those functions that are basically non-convex type of function. And one of such notion is the quasi-convexity. A function is said to be quasi-convex if the function f is such that the integral over a domain c, a domain omega of f at c is smaller than f, the integral of the function at c and grad of some function phi, which is a smooth function that is compactly supported. And there are additional properties such as being Lipschitz and having 0 on the boundary of omega. So if the Jensen inequality is satisfied, then the function will be said to be quasi-convex. So such property is an important property that implies the existence of the minimizer for the function that Morrey was trying to solve, because that property will lead to construct a sequence that is minimizing the functional, and that sequence will converge weakly to a minimum. But checking quasi-convexity is a difficult task. Why is that? Well, that's because first, the integral is of non-local type, as you can tell. And then it also involves the gradient of a vector value function. So it's not that it's difficult from the concept side, but the practical, its practical usefulness is the one, or the practical implementation of that criterion is the one that is difficult to do. But the good news is the quasi-convexity implies a less difficult type of convexity. It's called rank one convexity. And that type of convexity is this time a local properties, a property which can be checked more easily. Okay, yes, so I have over here the definition of what a rank one convex function is. And so if we have the rank one convexity, quasi-convexity that imply rank one convexity, the question is, can we also have rank one convexity that will imply quasi-convexity, in which case it will be easy for us to come back to the original Morrey problem, where we will find a criterion to say that the problem that you have at the beginning is well posed, meaning there is a local minimizer to such a functional, and which will be a good thing, again, in mechanics, in nonlinear mechanics, where these problems are of real interest. Okay.
Excuse me, please.
Yeah.
Is it obvious what the relation between capital N and lowercase n is? Whether which one is larger?
So the capital N, well, it's random, but the capital N, they indicate the N, the lowercase n and the capital M indicates the dimension that you will take the matrix F from.
I understand that, but I'm just wondering whether it's going to be a tall and skinny matrix, or wide and fat matrix, or square matrix.
So it can also be square matrix, but the problem we are interested in this context will be a square matrix, a 2x2 matrix.
Thanks.
But one of them, yes, thank you for the question. One of them was already addressed, which is not a square matrix, but a 2x3 matrix by Sverak, to provide the counterexample which illustrates Morrey conjecture. And it has been already proved, like 40 years after Morrey solved this type of problem. And the paper is available for sharing if that's that there are some interest. But the case that is of interest for this study is the planar case. We want to see if the function f is taking its foot from 2x2 matrix and has its outputs in R. Do we still have the rank one convexity that imply quasi-convexity? So it has been proved by Morrey, the Morrey conjecture. It didn't prove it. Morrey conjecture that such implication is not true. And the Sverak will illustrate that in higher dimension, but the 2x2 case is open. So what we want, yes, thank you very much. So what we want to do here is to be able to come up with a kind of solution that illustrates the Morrey conjecture. That's our objective. So for us to be able to do that, we need a function. So a function which, like we said, has the rank one convexity type of property. And we wanted to check if with such function, the Jensen inequality is satisfied or not. But there are several types of this function. Can you go back to the first one? Xinghao, thank you. So there are several potential candidates that are rank 1 convex function that can be candidate to illustrate the Morrey conjecture. The first one is proposed by Sverak himself, who already addressed this problem in higher dimension. And there is a second candidate, okay, by a book holder, and all of these functions are rank 1 type of function.
Excuse me, I'm so sorry to interrupt again. The absolute value of the matrix, is that a norm there?
It's a norm. It's a norm. It's regularly defined as the matrix norm. Yes, it is. Yes. Thank you for the question. Then can you go on the third candidate? Thank you very much. And then there is a third candidate function developed a couple of years ago by Alibert, Dacorogna, and Marcellini. And again, yes, it's made of these 2x2 matrix, and the bar represents here the norm, and the function involves both the norm and the determinant of the matrix. So the Dacorogna has proved that if the function is defined in a polynomial way like this, then for gamma that is between 2 and 4 divided by the root of 3, then the function is rank 1 convex. So it remains to see whether it is quasi-convex or not. If it is quasi-convex, but then we didn't, but then, well, for that family is still, the Morrey conjecture might not be true for such example. But if it is not quasi-convex, then we will have successfully illustrated the Morrey conjecture. So I wanted to point out that we were made aware of a recent other candidate function by Professor Neff at Aachen University in Germany. But it's very recently that we are aware of that and didn't study that in the detail. So, but it's worth pointing out that there is a fourth candidate to illustrate eventually the Morrey conjecture. So I was saying that we have a rank 1 convex function with the Dacorogna function, and we wanted to see if it is quasi-convex or non-quasi-convex. The analytic proof or analytic analysis is very difficult. It has been done, but it's still very difficult and not yielding to the solution. So numerical approach has been there are temptations of numerical approach to see if we can obtain the non-quasi-convexity. That was done by Dacorogna himself and Professor Grimaud. But the conclusion is that the function remains quasi-convex, at least from the numerical approach that we use. So the question is still open. So is the conjecture true or not? So can you go to the second slide? So thank you very much. So the Morrey conjecture problem is a very interesting one because it's connected to other type of problem. If we have the implication rank 1 convex, that implies quasi-convexity. It's not a bad thing. It's just that in that case, then we will have the fact that Averniak conjecture, which is true, Averniak conjecture is in harmonic analysis, where the Burlington-Alsford transform, which is in the context of it's used in the context of actually the quasi-conforming mapping. So if we have the rank 1 convexity that implies quasi-convexity, then, well, we will have fixed the sharp constant problem for the case of the Burlington-Alsford transform. And if Averniak conjecture is not true, then that will have implied by the converse logic that Morrey conjecture is just true. So that's one of the reasons why addressing the Morrey conjecture is interesting. It's also interesting to know that because it will have many impacts in the hyperelasticity. And besides that, study relationship between rank 1 convexity property and quasi-convexity might be of fundamental interest in vector value calculus or variation, with consequences such as variational fracture mechanics or in the shape optimization theory, differential equation, martingale, etc. So with this, I will introduce a little bit the work that we have done before Xinghao take the floor by saying that we will depart from the Dacorogna example function and run simulation with such example and see what are the results that we obtain. So Xinghao will present the parts and I'll come back to continue the rest.
Thank you, Koffi. I will introduce our simulations and numerical strategies. So as discussed before, we departed from the Dacorogna and Marcellini example function, which has a form given here. And our goal is to find a suitable value of a constant gamma that is between 2 and 4 divided by square root of 3, which is a range suggested by Dacorogna that his function f gamma is rank 1 convex. So we want to find the gamma within this range and also makes this f gamma not quasi-convex. So using the definition of quasi-convexity, we can reformulate the problem as finding a matrix C and a function phi. And the function phi is of Lipschitz type and vanishing on the boundary of the domain, which is unit square, so that the Jensen inequality is violated. And in other words, the Jensen integral here is negative. So we used several numerical strategies to tackle this problem, including first, a spatial discretization of the unit square, and second, a steepest descent gradient descent algorithm for our objective function j, and also suitably choosing the step size of the descent algorithm based on a line search algorithm. Based on line search algorithm with the information from the previous iterations. First, here is an illustration of our mesh discretization of the square domain from 0 to 1. Next, our intention to use this gradient descent algorithm was to fix a Koffi, was to fix a 2x2 matrix Koffi and check the Jensen integral for the approximated values for the function phi at all the nodes of the mesh mentioned before. The Jensen integral j can be computed by a double numerical integral over our domain, which we call it omega. The function phi here is updated in each iteration using this line search recursive formula at all the nodes. And in the gradient descent algorithm, our updating factor gk is obtained using the Gateau differentiation of the functional j with respect to the function phi. And the gradient of this Jensen function j is obtained in this form here. So this is the exact closed analytic form for the gradient of function j. We provided more detailed derivation steps in the appendix of our paper. We also notice that our function phi is of vector valued and the Koffi is a matrix. So we can decompose the gradient of function j and get the update functions for each entry of this vector valued function phi. And so this is a more thorough updating function that we can use in our numerical simulations. And next term is the suitable step size. So this step size tau k in the recursive formula is the step size defined as it is the case in the steepest gradient descent algorithm formulation. In order to evaluate this suitable step size tau k, we notice that it is equivalent to finding an alpha, which can make this second function here equal to 0. And we take the derivative here and we utilize the inner product. So we come up with this final equation here, and we know and we realize that the root of this function here is the suitable step size, and we can find the root. We can solve this function using a secant root finding method. Now, finally, to wrap up, this is a flowchart of our algorithm. As discussed before, we start off by creating a rectangular grid with the coordinates of the nodes stored in it. Next, we initialize a 2x2 matrix Xi and a constant gamma between a range that makes the function f gamma rank 1 convex. So we also define a vector-valued initial guess function, which we define as phi 0, and calculate its values on all the nodes of our mesh. So then with the updating formula, I'm sorry. So in the recursive steps, we first calculate the gradient of function j at all nodes. Then with this recursive formula here, we can update the values of function phi and modify them to satisfy the mentioned vanishing boundary conditions. And the next step is to use the information just derived to compute the next suitable step size using the secant root finding method. And before entering another round of iterations, we can calculate the current value of the Jensen integral, the Jensen function, and check whether it's positive or negative. And if the value remains positive, we can continue our iterations by updating the constant gamma, updating the function phi, and to search for more other potential candidates. And if the value becomes negative, we can see that we have found a set of parameters, gamma, phi, and Xi, that makes this function f gamma rank 1 convex, makes this f gamma not quasi-convex, so violating the Jensen integral. However, so we record the current gamma as a matrix Xi. However, we still want to continue our iterations so that we can construct more counterexamples.
Excuse me, please. You said in your algorithm that you're going to continue, go to step 4 until gamma is equal to 2.
Yes. So,
but you're in floating point arithmetic, right? How do you know? I mean, your gamma is a floating point number, and you're continually updating it. So how do you know that you can get an exact equality there? Gamma equals to 2.
We start gamma. So the upper bound of gamma is 4 divided by square root of 3. And we start our iterations with gamma assigned to this value.
Yeah, I understand, but I'm asking about the computation in floating point arithmetic as opposed to exact arithmetic.
Yeah, we use a approximated value of 4 divided by square root of 3. We only take like 4 digits after the decimal point.
Right, and you get gamma equals to 2 exactly in floating point arithmetic?
Yes. So we choose our maximum iterations to 1,000. So we can calculate the difference between our upper bound and lower bound.
I see. You're choosing a maximum iteration count. Thank you.
Yes. Okay. Thank you for the question. So our simulations at first did not produce any counterexamples, as the values of the function j, the Jensen function, were always positive. This has motivated us to modify our algorithm such that it can test Jensen equality for a larger number of the matrix Xi while keeping the core of our algorithm the same. More precisely, we decided to vary the values of the matrix Xi. The values of entries of Xi at each of the iterations of our steepest gradient descent method. And our numerical simulations with this modified algorithm reveal that for a given initial guess function phi 0, there is a test function phi k, a matrix Xi, and a constant gamma, for which the Dacorogna and Marcellini's example function f gamma is rank 1 convex, but the Jensen inequality is violated. So for example, with this initial guess function, phi 0, x, and y, this is a vector valued function, vector value sign function. And when gamma, for example, is located as 2.2723, and the Xi was randomized at this iteration at this value here, we can see that the value of the Jensen function is negative. And we also notice that because it will be discussed later, that right now the mesh size is 1/10. And here are some other examples, counterexamples with different initial guess functions to enter the iteration, and we can locate other gamma and Xi where the Jensen function is negative. And then, so in order to ensure the robustness of our method, we also tested it on a reduced mesh size, which h is 1/20. So for example, with the first initial guess function of the sign and the vector value function, right now, but the mesh size is smaller. So when gamma is 2.2574 and Xi is still between 0 and 1, all the entries are between 0 and 1, can also locate some Jensen values that is negative. So so the conclusion is that even if we reduce the mesh size of our initial geometry where the test functions are being approximated, we can still find that f gamma is rank-1 convex for some gamma, but not quasi-convex. And we also repeat another set of simulations with the same modified algorithms, but this time with higher order of magnitude for the entries of Xi. The similar results as previous were observed as we found suitable phi k, the constant gamma, and the function phi, for which Jensen inequality is violated. For example, so now the mesh size is still 1/10, and with this sign vector value function, we notice that all the entries of Xi are 10 times larger, or almost 10 times larger than the previous iteration. So now all the entries are between 0 and 10. So this is a range we manually set. And we can also say that we find some negative Jensen function values, but this time the values of this Jensen integral is larger, unless unlike the values that is very small in the previous iterations. So this confirms the robustness of the modifications we brought to our initial algorithm to address Morrey conjecture problem. And now we have found some candidate functions, and some of them are shown here. And then we decided that we can extract these parameter values that violate Jensen inequality and run some standard steepest descent algorithm on them in order to validate our method. Now my colleague Koffi will present the validations of our simulations and discuss the results.
Thank you very much, Xinghao. So like Xinghao was explaining, so the first algorithm that we have, it's like a pseudo gradient descent because we were not stopping it with any stop criterion, but the objective that we have was to have a large panoply of Xi that we can test, and with the hope that we will have the violation of the Jensen inequality to obtain the non-quasi-convexity. So while we keep working on it, we meet with Dacorogna himself, and he made a few suggestions with regard to that, so as we can validate the process that we are using. We decided to run a standard steepest descent with all of the example that we have that create the that creates the non-quasi-convexity, meaning the metric C, the gamma that is making the F gamma rank 1 convex, and for which we observe that the Jensen function was producing a negative value, whether it's a small or a large one. So when we do that, when we run the standard steepest descent simulation, so the function, the Jensen function was decreasing, and for the majority of them remain negative, so which confirm the non-quasi-convexity property that we obtain. Some of the examples are the one that we are showing over here. For some example, sample entry function that are of Lipschitz type. So there are many of them that we did. Actually, we did like 55 examples, and we didn't see any case where this was not working. It was staying non-quasi-convex. So while the function f gamma was rank 1 convex according to a rigorous proof made by Dacorogna and some of his co-workers a few decades ago. So I'm going to give a comparison with this work and the one that has been done in the past and say why is it that our seem to be different, because there has been this simulation, this type of simulation done by Dacorogna, Gambo, Rapage. So they were finding that it looked like, I mean, the reported result was quasi-convexity, but what they didn't have is an accurate gradient in the steepest descent algorithm. And we were attributing, we think that it might be those error that was, because they came up to a 12 digits precision close to find the negative Jensen, but they couldn't. So it might be because they didn't work with the accurate gradient. And besides that, they were changing the C like 1 or 2 times, and that's it. So that was really not enough, because you have to go toward the error of C, which we did here, because we could have reached out more than 1,000 C with our algorithm. So we believe that that's what brought maybe a chance to find those negative Jensen functions that we are providing, such that not only the function is rank 1 convex, but it's also non-quasi-convex, which we believe in that case is illustrating, at least from a numeric point of view, the Morrey Conjecture for the Dacorogna and Marcellini example function. So that's all I have to say. I don't have anything interesting to say outside of that. Then we are continuing this to come up with a rigorous analytic proof of our finding, so that we confirm that this will close the discussion on the Morrey Conjecture in the planar case. So I'll leave Xinghao conclude the work that he and I have done.
Yes. Okay. So thank you, Koffi. In summary, our work is the first successful implementation of a numerical strategy over the past 30 years to address Morrey's conjecture problem. Also, we noticed that in some of the numerical experiments done by Professor Dacorogna almost 20 years ago, they should have obtained some negative values of the function j, such that the function f gamma is not quasi-convex. However, as discussed by Koffi before, they were only able to obtain j equals 0 up to 12 precision digits, so which we claim to be a numerical error, coming from an additional discretization of the first variation of j they used. We believe that we have corrected this with our exact closed form expression of this variation. So that is the gradient of the function of j. And also the randomization we introduced into our algorithm, into our simulations of the matrix C at each iteration is the main difference between our work and previous attempts by other people. So by doing so, we want to explore a larger space of possibilities. As we see from the results, a vast majority of the iterations fail to produce a negative function j. But we still, however, we still succeed in finding a few sets of matrix C and function phi and the constant gamma at which the Jensen inequality is violated. Thus, it provides numerical evidence that f gamma is rank 1 convex, but not quasi-convex. And based on these findings, I'm excited to share with you our plans for future research that will expand upon and build upon the knowledge we have gained thus far. So first, we want to explore more analytic work, such as the connections of the Morrey conjecture with the Enakoutsa conjecture, as discussed by Koffi, so that more analytic work can support our claim. So also, instead of sticking to the Lipschitz type function and the vanishing boundary conditions, we can also use other boundary conditions. And Professor Sverak, he suggested that we can use things like periodic boundary conditions to run the simulations we met a few days ago. And also, in addition, furthermore, we want to explore if there are other local properties that can be used to characterize this weakly lower semi-continuity. And we want to see if these local properties can validate our denying of the equivalency between the quasi-convexity and Riemann convexity. And also how the properties will affect the convex optimization problem, especially for quasi-convex programming. And on a more application side, we can also apply, Morrey's conjecture is also helpful for developing constitutive models for microstructure materials. And also, Koffi just mentioned that Professor Neff in Germany just came up with a new example function. And in his paper, and he also used techniques such as machine learning. And we also want to explore these techniques such as machine learning to see if they can help us to address Morrey conjecture. And thank you again, Professor Ji, for inviting us to present our work to your department at North Carolina State University. Also, thanks everyone for paying attention to our presentation. We will be very happy to take any questions you may have about our work. Thank you.
Thank you very much, Xinghao and Koffi. Do we have any questions from the audience?
Yeah, I would like to ask a question with regard to your second bullet in the summary. I still like to emphasize you're operating in floating point arithmetic. So, you know, you're not going to get 0 to infinite number of digits. You're lucky if you get j equals 10 to the minus 16. So, and also it's not clear to me that necessarily the discretization is at fault, because I'm not sure whether your algorithm is numerically stable. So in order to really validate your claim, you should also do a numerical analysis of the algorithm that you have. And also your matrices C seem to be strongly diagonally dominant. Could you choose a diagonal matrix?
So the matrix that we are obtaining, to start with the last question, if I may, the matrix that we are obtaining are not the one that we generate, but it's the one that are coming from the simulation that we are using there. So it's very difficult, because we can be trying those metrics in the first round of simulation we made. When we try metrics here and there, it's very difficult to obtain the non-quasi-convexity. But yeah, we will be trying a diagonal. But for some of the results that we have, can you go to Xinghao? Can you show the 9 points and the one that was looking a little bit diagonal, not too much for diagonal, the one we showed?
Well, they're all strongly diagonally dominant, these matrices, right? All of them.
Yeah, yes. But so we wanted to try a few things here and there, but for the conjecture to be illustrated, we only need one.
But again, you know, you're operating in floating point arithmetic, so just because you're going to evaluate an exact expression does not mean that your algorithm is necessarily more accurate.
Yeah, I agree with that. And actually, if you can scroll back the slides to the case where the entries of size were smaller, you had 2 slides there. Can you scroll back a little bit? Yeah, so this is with mesh 1/20, right? And you see that your negativity, so to speak, of the functional j is in the 3rd or 4th digit, right? And if you go 1 slide back, can you, it's 1 over, no, back. Yeah, here. So it's 1/10, and here you have in the 2nd digit. So my guess would be that if you continue along these lines and do 1/30 or 1/50 or 1/100, you will be moving this negative, like, you know, where you have this negative value further out. And it by no means clear that, like, you know, that because you are, there are all sorts of approximations. There's round off, as Professor Gibson mentioned, and also the dependency on your discretization, and also the integral. What quadrature are you using for the integral? I mean, you have to integrate numerically. I mean, the formula for the integration is not exact.
Yes.
Right?
No,
So there are like, there is a sort of a layer.
We are not claiming that there is no approximation that is involved. But what you are saying is if we randomize this C, we are not saying that the result is mesh independent. But when you randomize it, the discretization leads to a negative Jensen inequality.
But this negative depends on your discretization parameters. So you do what you are computing is not exactly what your analytical expressions are. You are computing an approximation, and it's sort of, okay, just for the sake of curiosity, why don't you just take h over 1 over 40 and see everything else the same? Like on this slide, you have h 1 over 10, 1 over 20, take 1 over 40 and see what happens. What will be the magnitude of those negative values of your functional?
Yeah, we are happy to to check a lot of things on the simulation that are made over here, but there will always be a round of approximation, which we want to measure the error that can be brought by the approximation size of this.
Yes, there will always be roundoff, but you have to make sure that the roundoff error doesn't overwhelm your final result.
Absolutely. No,
the algorithm is numerically stable, right? And that the discretization is appropriate.
I agree. That's why as a validation purpose, we choose those values that we think creates the negative parts for both the lower cases and the higher one, and run a regular steepest descent to see if. So we have the Jensen that is exactly descending as the gradient should be, and are they remaining negative in a standard steepest descent? So, but yeah, I mean, those are things that we are exploring, the precision of the scheme that we have, how much error the approximation is introducing. And is the error too much for this claim? So we are exploring all of those contexts. But for now, it's what we are having with the type of validation we have, but it's just giving us this type of conclusion.
And yes, also, if I may add up to Koffi's answer, and the professor just suggested that we can use a diagonal matrix, since the matrix here are all of a strong diagonal.
No, I didn't suggest, I was just wondering, that's all.
Yeah, I mean, we did run a few iterations with diagonal matrix, and it was suggested in Dacorogna's paper, and the matrix we used is in the form 1, 0, 0, and square root of 3. So with this matrix and without the randomization, we, like Dacorogna, we were not able to construct any negative values. So this is why we decided to, okay, we can randomize. And yes, this is a very, a special trend that they are all of strong diagonal matrices.
Okay, do we have any other questions or comments for the speakers? Okay, thank you. So I'm gonna stop the recording and we can discuss a bit more if you would like.